record. Okay. Shrikant suggests that we pipe means the key value pair separator, right? Word 1, word 2, word 2, word 3, right? Awesome. Awesome. Okay. Okay. Good. Good. So did everybody got this approach? No. All right. So basically your mapper is in this form. This is what Naveen is saying, and Naveen and Srikant, that take the text, form these pairs. How are you? Right? And then Ram happy birthday to you. And then reducer will do the frequency analysis. Right? Do you see any problems with this approach? I can see multiple problems in this approach. This is a standard way of forming the tuples. I mean, the problem statement is standard, but the approach is not does not look good to me. Yes, Apurv, are we on the same page? No, Nitish. Right. So first problem, as Viran is saying, that you need to identify the end of sentences, right? You need to identify the end of sentences. That is one problem. Excellent. The next problem, do you see any other problem? Right. If the values will be a huge list which we need to store, there'll be a lot of memory. Yes, yes. Why here is why is this memory a problem here? Because of mainly this reason, because you got to do the analysis of the values, right? You got to do the analysis of the values. So the keyword, whatever keywords come after how, say there are 10,000 keyword, then 10,000 words that come after how, right? Now you got to do the analysis of those keywords. What analysis? Basically, you need to do the word count of those words, right? You need to do the word count of those words, and that is going to be costly affair, right? Good, good. So if you do the frequency analysis in memory, it is going to be a problem. Cool. Yes. Do you see any other problems in this approach, Siva? All right. So basically, these are the three problems. First one is computation of frequency can be further map redded. Right. We need to find. Right. We still need to find top five. And to find the top five, we we need to do the computation, right? We need to first do the word count or do the frequency analysis in one way or the another, right? And therefore that will require a lot of time. So basically, top five as in we need to find the top five words that follow how, that follow are, that follow you, and so on. For each word existing in your text, you need to find out what are the top five words that follow each word. Okay? In the whole big text. That is the problem. So, so So these are the problems basically. First is computation of frequency need to be map reduced further because if you if you try to compute the values, if you try to compute the try to count the words, the frequency analysis in the memory of the values, then you are gone for a toss. That should have been part of the map reduce. Second is the last word of the line should pair with the first word of the next line. If you see, so we have to look for the sentence completion, not the line completion. That is another difficult challenge. Okay. Now, to do both of these, first one is comparatively easy. First one is comparatively easy in the sense that you form the tuple key value pair such that the key is how dash r and the value is 1. Okay. Now you do the counting part here. All right. So anybody has a suggestion for this? So let's say we are okay with line itself, and you just have to do the fix the this computation problem. What will you do? Anybody? Let's say end of the line is handled. Your input reader is getting your map is getting sentence by sentence instead of line by line. What is it that you can do? How would you correct the frequency problem? Because it is going, we cannot do that in memory. Okay. Okay. In terms of MapReduce, Srivasant. Have every word in a line and save to the file. Copy the file and delete the first line. Okay. Have every word in a line. Okay. Copy the file and delete the first line. Delete the first line. Join the two files with the line number as the key. Okay. This is an interesting approach. Let me just think about it. Okay. Okay. Have every word in a lines. Oh, I did not get that at all. Okay, let me read Naveen's approach. Keep the reference of the previous word. Keep the reference of previous word always. This will preserve continuity. Okay. Form the key with the word and next word combination. That is okay, Avitesh. Yeah. Okay. Each key value should be the output of the mapper. Sort them. Count the keys through the reducer. And again use mapper based on greatest count. Okay. All right. All right. Okay. So let me go ahead. All right. Looks like that approach is not here. All right. So the problem is little difficult to solve. Let's first think about the computation of frequency one, right? So we have got word one. Okay. Let's say in the first shot, you form the keys such that first word, your key is your key is first word underscore second word. All right. First word underscore second word. That is your key in the first one. Then and the value is just one. Right. Now this will give us a big list of things like how and then r is 10 times how underscore is say 15 times. These are just example and so on, right? So in reduce, so this is mapper. So in the first sort, mapper did this. All right, so let me just increase the font. So in the first shot, mapper did form the key based on first word and second word and so on, right? So after this exercise, and let me take the example here. So basically here I'm saying how underscore r becomes the key, r underscore u becomes the key, and so on. And the value is just 111. All right. Now, as you can see this, so at the end of this exercise, okay. Oh, delimiter, that's what you meant. Okay, okay. I thought you by pipe you mean to say the key and the value. Good, good, good. Then your approach was right, right? Now once you are done with this, right? Once you're done with this, and how do, okay, and so on, right? The next time in the next mapper, you keep the key as frequency underscore first word, okay, and the value as second word, right? After this, and in the reduce phase, you just, okay. So basically mapper will return something of this sort, 10 10 underscore how, and r 15 underscore how, and then is, and so on, right? And there in the reduce phase, when you are given each key, so reduce phase doesn't have to do anything at all in this case, right? Because this will not lead to many, or actually this will lead to many. In the reduce phase, in this reduce phase, you don't reduce anything, you just print out as is, okay? In the reduce phase, you can print out as is. Right, you can keep the frequency as second, that will also do good. It won't be much of a difference. It won't, because see in this other case, all these keys will anyway be together. Okay, what he's suggesting, that's also a good idea, right? This is what you are suggesting, right? And here, all we want here is, so the order will be the same here as well as here. Basically, we are saying that our key is a tuple. Our key is a tuple of two things. For one is a number and other is a word. Okay. So we need to get sorting done based on the word, based on the lexical order in case of a string, and numeric order in case of a number. All right. And why do we, and that we need to implement properly using Java code. Okay. Because in here Hadoop will try to think of it as a string. Okay. And now as in the next map phase, the next third map phase, what you do is you keep on ignoring, or what we can do is in the reduce phase, if we are having, we can actually run the reduce phase like a streaming job. Okay, let's do this part as a streaming job. Okay, streaming job. Okay, and in the reduce phase, because you will get all of these things in a sequence from top to down. The difference between the streaming job and the normal job is, in the normal job, by default you get only the one key in the reducer, while in case of a streaming job you get the whole content, whole output by yourself. All right, there in the reduce phase, keep keep top 5 of each. That's all. In the reduce phase itself you can do this. Okay, because in reduce phase you get the whole content. Oh, right. Actually, Praveen is right. Now I realize what he is meant to say. So what he meant to say that in case you have 11 here and there is a ABC, it will get into this. Yeah, you are right, Praveen. Thank you. Now I got it. You are right. So it should be like this only. All right. It should be this only. Good, good. You're right, Praveen. Okay. How about word one underscore frequency underscore word two? Word one underscore word two frequency word two for the second mapper. Wouldn't make much of a difference. Wouldn't make much of a difference. That's also correct. Right? Good, 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 good. All right. So yes. So we will actually keep it this way because if other number can get into between this. Okay. And in the reduce phase, you can keep just top 5 of each. Okay, and this one is a streaming job, and the quality of the streaming job is reduce gets the whole content in a single shot. Okay, so the first part can also be a reduced job and second part can also be a reduced job, but so using this you do not have to do any sorting or try to find out the uniqueness and all of the magic. You do not have to do that. Okay, here reduce phase, in the reduce phase it will just keep on keeping the words until the first word changes to another word. Okay, or first word is there, like say how is 5 times, that's all. Okay, after that it will keep on skipping that. All right, so that is a beautiful part of the streaming job, that it gets the whole content. So that is one thing. So this way you can actually do the computation of frequency further map reduced. All right, now this second part is far more tricky than we think. All right, why? Because map reduce by default gives line by line text to your mapper. Okay, whether it's a streaming job, non-streaming job, it gives line by line input to your mapper. Okay, you cannot go beyond that. So we will have to modify the behavior of Hadoop to give your mapper the sentence by sentence input instead of line by line input, and that is going to be a little complex. Okay, that is going to be a little complex. All right, and this can get further more complex if you try to take into account the double quotes, single quotes, comma, and all this stuff. Then you get into the natural language processing part. Okay, what if there is a comma and you want to say that anything that exists inside double quotes should not couple with the other words outside, right? The one which is inside the double quotes is a sentence in itself. Right. So Srikant's doubt is genuine. If we get like, let's say we got how underscore one, how underscore two. Okay. Now in the reduce phase, as I was telling, because it's a streaming job, I was suggesting that let's keep a streaming job over here. In the case of a streaming job, we can easily, because streaming job gives a single reduce output. Okay. And and i- this streaming job gives the whole content from line by line to the reduce phase. Okay. So reduce acts as if it's reading the whole content from top to bottom. Unlike the reduce phase of your normal Java MapReduce, where reduce only gets key and a list of values. All right. So the moment it hits, the moment it hits, okay, and here you need to make sure that this is ordered in descending order. Okay, we need to also specify in the streaming job itself that I forgot to check. All right. Okay. So all right. And in the reduce phase, you'll get this text. You keep on going as long as you are getting the same word. Keep on going, and the moment you hit five top, you just ignore everything after that. All right. Or you can do the other way also. You keep on going, just retain last top five words. That's all. Okay. And keep on popping out the words from your list. Okay. From top to bottom, you create a queue of five size. You keep on pushing the words into the queue. Okay. You keep so reduce phase will get the whole text line by line, right? So you since this is in ascending order, we can actually do it in ascending order itself. So as soon as you get a word, you keep on pushing it into that, and then keep on pushing it that word as long as the word is not changing. The first word is not changing. You keep on pushing into the queue, and in case the queue goes beyond 5, remove the first inserted word. So always queue will act like a window containing only the last 5 words. All right. And the moment you hit another word, say here how, let's say another word comes in here and it says 12. Okay. And at that moment of time, you just print the result onto the output. Okay. Okay, I'll show you. So first, you added this to the queue. Okay. Let's say this is my word one. Then you added this also to the queue because how is still the same. How has not changed. You added this. Then you added this also to the queue. Then you added this also to the queue. Then added this also to the queue. And now the queue you and the moment the queue is full and you're trying to push one more word like w6, this will be removed, this will be deleted from the queue. So your queue contains only these words right now. Okay, these words right now. All right. So only the last five words you will retain and rest you will let it go. Okay. You're scanning from top to bottom and retaining only last five words. That's all. Yeah, you can think of queue as an array here. Basically a window over the last five words. Okay? And the moment you hit another word, here we have hit howdy, you print how dash all these five words. That's all. Okay? How and then all these five words. All right? So that's why I was saying reduce job with a single reduce. Okay? So reduce job with a single reduce. Otherwise, how one will go to one node and how two will go to some other node, right? A streaming job with a single reduce. Okay? Let me just mark it. Cool. So this is the approach we will take. Okay. Okay. So what you do is first you got this this file as the output of the previous job, right? This as the output of the previous job, right? Now you create another uh, program, maybe shell command or Python command, which basically generates this key. Okay. Now then you write a reduce phase. Reduce phase can be in Python, it can be in shell, which basically keeps only the last five words for each word. Okay. Or maybe a Java program, whatever you want to keep here. Okay. And it should be actually possible in the in the Java MapReduce itself. I'll look into it. How can the reduce get the whole content as a single file? Okay, it should be possible. Just there should be a way to handle that thing. Okay, just need to explore a bit. Okay, streaming job you can execute the way we have talked earlier, and this also you can execute like a Java program. All right. Okay. So you guys try to attempt it, okay? And I will also share my code once you guys are finished, okay? And then you can see the approaches and that will give you more idea. All right? All right. So here the idea I wanted to portray more than the computation of the frequency was the sentence computation. Okay? Sentence computation is little tricky process and we will talk about it. Okay? There you need to configure your Hadoop in order to read sentence by sentence. Okay, now let's move. All right, Naveen, not right. Okay, yep. So, oh, you are answering the question, I thought. Okay, Srikant's point is, can't we use our regex for identifying dot and ignore it? No, actually, Srikant, the default behavior of Hadoop is to give you only one line. So your map job has no visibility into the next line. Okay? So your map function will get only one line at a time. And that's where the problem lies. We need to convince Hadoop to give us more than one line, and then we form our own input. That is something which requires more. All right, good. So data generated by mapper is given to reducer and then it is sorted and shuffled. So everybody, answer is no. Good, good. Anybody has a doubt about this? I can clarify. The output of the mapper is first shuffled and sorted and shuffled actually, and then reduce are called. Okay. Okay, never mind. So it's sorted, shuffled, sorted and merged. All right. Now the next question. The mapper can only generate a single key value pair for an input. Yes or no? For each line, when we say input value, right? For each line, can mapper generate multiple key value pairs, or can it generate single? So here the mapper can only generate single key value pair for an input value. Is that correct? Are you sure, guys? No. It can generate as many key value pairs as it wants. Input value is a line, right? Yes, it can generate more than one. So line is given, you remember our word count example? Each line generated at least 10 key value pairs, right? Equal to number of words in a line. Mapper can generate as many key value pair as it wants. All right. Now, by default, there is only one reducer. By default, there is only one reducer in case of a streaming job. Good. Yes, by default, there is a reducer, but there is a option called MapRed.reduce tasks, which can help you fine tune number of reducers. All right. All right. Okay. Okay. This one or before that one, Srikant? Vishal, this one? This one? Yes. So each line when is given to MapReduce can generate, your mapper can spit as many key value pairs as it wants. It all depends on you. Okay. Now it's okay, Vishal? Is it clear? Okay. So have a look at this. Now, okay, let me just jump back a bit. So if you look at this, the mapper actually took the single line and generated one, two, three, four keys without any value. right? Similar was the case earlier. Okay. Here, when we say something like this, okay, and when we replace a space with a new line, we are actually generating multiple key value pairs. All right. So on the Java line of code, maybe this will help you a little bit. Although I'm jumping a bit ahead, we will come back to it again in a minute. Okay, so here, if you see what is mapper doing, it's taking a line and converting into multiple line by replacing the space with the new line, which means it's converting a single line into multiple lines, and each line acts as a key value pair. Okay, it's just that since there is nothing else, so value is null, key has something. Okay, now let's look at our mapper. Okay, so if you look at it, this is our mapper job. It has got a key and a value from the system. The key is byte count by default, the system gives it, and value is the line. So we have splitted the value into by tab and spaces. Now we have got so many words in particular line, and for each word we have given generated this as the key value pairs. Okay, so for each word we have generated multiple key value pairs. Okay, clear now? No? Okay, so for each line, for all anything, if you want to generate a billion key value pairs, it's all up to you. You put a for loop over there and keep on spitting the key value pairs as many as you want. All right. Can NetBeans be also used for Java? Definitely, yes. It can also be used. There is nothing special here because it does not have any Eclipse add-on per se. Okay, it's pure Java. Had it been an add-on like Android, it could have been difficult, but it's pure Java. Good, good. All right, now we are okay. This question: What is the role of job tracker? Executing MapReduce logic or delegate MapReduce logic to task tracker? Quick, quick, quick. Good, good. The map logic is executed preferably on the nodes that have. Okay, I'm sorry. Okay. Now, the map logic is executed preferably on the nodes that have required data. Good. Preferably, not necessary, preferably. You're right, Apur. So Hadoop prefers to execute your map logic on the nodes that have data or closer to those nodes. Okay. Now, quick question. The whole chunk available on a node is fed to the mapper, yes or no? So let me ask you this question again. So the whole block, whatever available on a node, is fed to the mapper, correct or wrong? Okay. This is a little tricky question because that is what we are going to discuss today. Okay. Now, do you think our mapper, see the our all of our mappers got the whole line into the mapper's input? Do you think there was no block in which the line was sliced? Did HDFS honor line by line? Did HDFS make sure that while slicing the block, it should not split the line? S- Lines could be sliced, right? Because HDFS doesn't care. HDFS doesn't care whether it's in middle of line, middle of sentence, middle of word. It doesn't care. It just slices it the moment the byte count reaches to 128 MB. Okay, so it just ruthlessly slashes the file from that point, right? Whether it's in middle of word, middle of line, middle of you know sentence, it doesn't care. So the whole chunk, whatever is available on that particular node, might have incomplete word, incomplete line. So it cannot be fed completely as is to the mapper, right? Therefore, and this is what we are going to discuss today. The answer is no. The input is split into input splits, and part of which is transferred to other nodes, to other mappers. Okay. Okay. So the line can contain maximum of 28. When I said that, all I wanted to say that no, okay, there's some confusion. So each block can contain at most 128 MB. This is what I wanted to say. Okay, maybe I confused somewhere. Okay, okay. So so each block, right? Yeah, we'll be discussing that in a bit. I'll just show you a code and then you can have a look at it. All right. And although I don't have the complete, I've not finished the code which is for sentence by sentence processing, but we'll do that quickly. Okay. All right. So HDFS has its own behavior. HDFS doesn't care whether it's your middle of sentence, middle of line, middle of word. It doesn't care. It just slices it from there. It's the duty of your Hadoop MapReduce, who will basically read what it wants. Okay. So the way the default Hadoop reader has done line by line processing for you, you might want to do sentence by sentence processing, right? Now, before moving further, let me ask few more questions. Where does Hadoop store the result of reducer? Okay, good, good. No, it doesn't store in the local file system. You remember that part 00001 which we saw in where the result was located? That was in HDFS. Okay, all right. And where does it store intermediate data of mapper task? Whatever mapper is giving out? HDFS file system or RAM? Quickly, which one out of three? Okay, this is a bit tricky. Okay, this is a bit tricky. So first it puts it into the RAM, and RAM is quickly parsed onto the disk. Okay, each mapper's task is actually being pushed into the RAM, and that RAM is immediately parsed to the file system. Okay, so the local file system is the right answer. Right. Okay. So are you trying to? I did not get this. RAM minus disk is local file system. No, no, no. Uh, Basically, yeah, RAM to disk. Yeah, that is correct. All right, local file system. Good, good. Now, today we are going to discuss something which is important. We have so far discussed streaming job, but we haven't touched upon Java code so far. Today we are going to discuss that part. And so first question that arises is why Java, right? And why do we need to support Java? Why do we need to write the code in Java? And second is that so and then we'll get into the details of writing MapReduce in Java. Okay. So most importantly, we write the code in Java is because Java has got primary support. Okay. The basic behavior if you have to alter of Hadoop, then you got to write it in Java. Basic behavior as in instead of reading line by line, just give me the whole file, or instead of reading line by line, let me just handle it sentence by sentence, or whatever format do you want, 2 lines at a time, 10 lines at a time, or whatever system you want. Okay, so those kind of behavior you can modify using Java. That's the only reason we use. Okay, I'll make it available. So here it is. Okay, so it'll be available quickly onto the course page. Okay, fmake, and it'll be available on the LMS course page. From there you can download. I'll give the whole project. Okay, and with the libraries as well. Okay, so first you install Eclipse, then you create a Java project, then add these libraries: Hadoop MapReduce client core and Hadoop common.jar, and then change the JDK from 7 to 6. Okay, and then change the compiler Java compiler setting to 1.6. Okay, so I have already done that part. Not much, not much. That's okay. Any version of Eclipse will do because we are not trying to specify any particular thing. Just make sure that in Eclipse you have the Java IDE. Okay, not the Android one. Java IDE. Okay. Now, so I'll share the project, I mean this whole thing quickly just after this session, or you can have a look at my courses. Let me just go into a little older one. So if you want it immediately, I've just shared the link to you, and you basically you can download it. So it has got all the libraries, whatever you require. It has got all the libraries, and it has got this project. Okay. You can simply import this project also if you want. Otherwise, you can just keep on using these libraries as you wish. Okay. Okay. Now, as you can see clearly here, so first you create a fresh Java project, add these libraries, and then change the JDK to from 7 to 6, and then change the Java compiler settings to 1.6. Always, whenever you're coding in Java or any programming language, make sure that you have, you know, proper. You try to support as much as backward compatibility as possible. Okay, as a good developer, you need to think in terms of, if you're building a product, you need to think in terms of that you support the minimum possible Java. Okay, so if you compile in the Java 6, it won't run in Java 5. If somebody is having the older version of JRE, it won't run in that. So you generally try to be as conservative as possible when it comes to compiling your code against a JRE. All right. Now the first step. So I've already done it. I've already created my project, and so first step to do is, once you have created a fresh project, just add all the libraries available in that project. Okay, just add all the libraries available in that zip file to your project. Change the JDK from 7 to 6. You can do it quickly using here from properties page, and here there is a library, and I just changed it to Java 6. Okay. All right. Now the next step would be to create a mapper. And what does a mapper look like? A mapper looks like this. Okay, let me just close everything. Close all. And here we go. All right. So we have got this mapper, nice mapper. We've got this mapper. Basically a stub mapper, whatever name you want to give it, you can give it my mapper and word count, whatever you want to give it. It should extend a abstract class called mapper, and also specify these template versions where you tell that I'm extending this mapper for these with these four data type. And what does it mean? This is what mapper will get. Our mapper will get the input in these two format, and these are the two data types in which it has to give out the data. Okay, so since we have to give word count, the key is going to be a string and the value is going to be a number. Therefore key is text and value is a long. Okay, and these are the data types actually done by Hadoop for you. I mean, for a new kind of a new data types, instead of a standard string, it is text. Instead of normal long, it's long writable. Okay, they were facing some challenge with existing Java data types, so they created new kind of a data types. It is compatible with Java 1.7. It just that it is a good manners to keep your Java code to compile onto the lower version. Okay, if you compile your code with Java 1.7, it will not run on JRE 1.6. Okay, otherwise it doesn't have any problem per se. Yeah, long writable is basically a serializable class. Okay, and is extending writable from Hadoop and implements a serializable. It's that way. Okay, so you can have a look at that one also. Okay, so basically it's public and it's a writable comparable, implements writable comparable, and so on. No, not that. There is some more. Okay, all right. Now you can have a look at the documentation, JDK documentation of Hadoop. All right. Now this is okay. This is like customary. This is something which we do as part of the process. This is also, you put an override here and then say this is my map. And remember, the same data type, whatever you define here, same will go here. These first two values will come here, right? Same data types. Now your map is getting two things from the system. One is key, other is value. Here the key is basically byte count. Okay, key is basically a byte count. On what byte is your input, not line number, because line number is not possible per se. So the value is actually your line. Now you take this line, convert that into a string, then split it on basis of space and tab, and there you get the array of words. So this, because this is your line. Okay, now you split it the line by space and tab, and there you get the whole list of words, and you iterated over these words and the printed each word with a value called 1. So each word is your key and a value is 1. All right. Okay, and if you want to look at it here, you can look at it here. So this is something we have implemented. Are you okay? Okay, context is the, context is a variable provided by Java in which you put your output. Okay, instead of giving it to standard output, printing it to the screen, you are putting your stuff into the context. Okay, so this context is what will carry your data from mapper to the Hadoop system, where it will get sorted, and then the it will be provided to the reduce function. Okay, is everybody okay with this code? Even if you haven't gone through the Java thing, it's only the template which will be look little awkward, so you can ignore these angle brackets for time being. All you are doing is writing a map function which was given the input line. This is the input line which was given, and a variable called context, which is which is provided by the environment. So you process your line, put the output in context. That is the whole idea. Okay, and you can print as many as key value pairs as you want. Okay, here we are putting word 1, then numeric 1, then next word, and then numeric 2, the next word numeric 3, and so not numeric 3, not numeric 3, it's only 1. It's always 1 here. Okay, sorry for that. Yeah. Okay, how do you link your Java with Hadoop? We don't link Java with Hadoop. We'll talk about it in a minute. All right, and then you write your step reducer. Okay, you write your step reducer like this. Okay, reducer in the same fashion we define our input output data type. These are input expected and these are the output expected. Okay, these are the data types which we need to strictly define in Java all the time. That I'm expecting a key with a for type text, I'm expecting the value of type 1, and then I'm expected to give the output in a string format, and I'm expected to give the sum, which is a number. Okay, so what we are doing as a part of map, we took a line, split it by spaces, and converted key value pairs. So each word we are trying to count. Now here we get what we get. Here we get as part of reduce, your reduce function, this is where your code goes. Okay, your reduce function will get a key and an array of values, an array of values. This is iterable of values. Okay, which is equivalent to saying a big array. If you read it all, it's not, basically iterable is provided because it's not in memory. Okay, it's just a pointer to that array. You can read it one by one and then print it here like this. So all this code is doing is going through these values, summing them up. That's all. Okay, because these values are nothing but an array of ones. Count and sum both are equivalent for this. Okay, so after you are done, just like what we did it in mapper, we did a write to the context key and the summation. So that gives us the word count. All right. Now once you are done writing a reducer, you create something called a driver like this. A driver is what? A job. Basically, first you create a job with a config. Yes, this is the reducer which will be called for each key. All right. All right. So here, if you see this job, it's basically we created this. And important part right now is these two lines. Okay. For this job, we are saying this is my class which I just wrote called mapper, and this is my reducer. Okay, and once you are done, you get exit system.exit. If you notice, we are basically exiting the whole virtual machine over here. All right, it waits for the job completion and then it finishes. And once you are done with it, once you are done with this, what you do is, so here also notice, I'll show you some more things here. Okay, here there is something called, here step driver is there. Now step driver is something like this. Okay, here you need to pay attention to this one, and also number of tasks, right? Let's say number of tasks right now is 2. Just for the heck of it, we have kept it 2. All right, and all it does is it takes input file output file, and it puts those input file output file again into the job, and then it runs it. So now let's just create export and go to jar, and then we have this and say word count. So this is something you need to specify, and this is where your jar is created. So this will, what we are trying to do is we are basically packing our whole code, compiled code. We are basically packing up our whole code into a jar. If you see, All right. So, all right. SCP. Now, whatever we have just done, we have basically created the jar which contains all of our code under a file called word count.jar, which is what we have just created. Now we'll copy it to the server. All right, we'll copy it to the server by name. You can use SCP, and also in case of a okay, in case of I'm just copying it to my asgiri folder. Okay, so I've copied it to my asgiri folder into onto my server, and this is not into hdfs, this is just on the hadoop one. Okay, here is that file which we have just created. Now to execute this, all you need to do is hadoop jar and word count. Let's see what happens. Okay, so it says that please provide the main class name also. Okay, and the main class name is this driver. The driver is the main class name, and it is inside a package called sg. Let me just put sg also. All right, so it's saying that provide the input directory and output directory. Okay, the input directory is asgiri slash input slash, that's all. No, it is word count and input. All right, and let's say asgiri slash word count slash output, and let's call it Java Hadoop, Java MapReduce. Okay, so I provided it input directory, and I provided an output directory. That's where it's going to save the output. And let's have a look at our HDFS. What's going on with our HDFS? So saying running MapReduce 0%, 0%, and let's see if it completes. Now it says, okay, status failed. One of the reducers have failed. One of the mappers have failed. Never mind. Okay, so again, something is seriously wrong. We need to look at it. Okay, we need to look at it. So here is our word count, and we are expecting in output and then Java MR. Nothing has come out. Okay, this is again trying. Let's see what. Okay, it has finally done. Okay, because there were some problems on some of the node, so it gave an error and then tried to do something. Let's see what is there. Good, good. And also note here that we have defined that there are two map reduce tasks. If we defined only one, then there would be only one file here. There are two files here. One this, it has some data. Okay, so the last block is up to j in the first part, and in the second part, the 001 part, it starts from the k. All right, it starts from the k. Are you okay on this? All right. So it has automatically split it. I don't know on what basis, probably alphabetic basis, and divided the task into two. Okay. Just let me have a look. Oh, I have defined a partitioner. Okay, I have defined a partitioner here. I've defined a partitioner on K. That is why it has split it on K. Let's just ignore that part for now. We'll talk about the partitioner again. Is it? Yes, it is running on two reducers over here. Okay. So if we just comment out our partitioner and we just comment this out, it will be only one. Okay. So does it make sense to you? We'll talk about partitioner. Don't worry. Don't worry. Don't worry. Yeah. Okay. So till here, everybody is comfortable, or does it look so dauntingly horrible? Two reducers do not mean that there should be two machines. If there is only one machine available, then it can't do anything other than running the two reducers on the same machine. Okay. But if there are two machines, then it will prefer to run those two reducers at two machines, because the overall objective of running making two reducers is to distribute work, computational work, which is reducer is going to do, to two multiple machines. The only reason we create reducer is for multiple reducer is for optimization reasons. We want the multiple machines to take help in the processing. Okay. Can we work on two keys in one reducer? Yes, but we cannot have one key on two reducers. The same key, all the values will be processed by the same reducer. Okay. Here it has two reducers, right? If you see, we did two reducers and therefore it resulted in two files. It resulted in two files, part 1, part 2. But it has got how many keys? Each reducer had got so many keys, right? Thousands of keys. So a reducer can process two keys, single reducer node. We are not talking about reduce function. We are not talking about this reduce function, because this reduce function has got only one key at a time to form. Oh, okay. Here it will reduce function will only get one key, but reducer, the instance of the reducer is only one. Okay, for all the keys, for all the keys on that machine. Wait for completion is meant for waiting for the process to finish and only then exit. Don't exit before that. If it exits before that, the whole virtual machine which was running will get killed. Okay, sound sensible to you? So this is how you run your Java program. So export your code, copy to the server, run it using the following command, and and in case, let's say you are using your own templates, or you are using your own internal library, or you are using some other command. Say you are trying to send email or something, right? Using Java mail program. In those cases, you can and you can use this minus libjar and a comma separated files of jar, which will basically take all these jars and deploy on all the nodes where mapper is going to run or reducer is going to run. Okay. just like file in case of a streaming job, this libjar helps you upload your own jars, right? Because in your code it could be anything, right? In your map code or java reduce code, it could be any legacy code also, right? And therefore it makes sense to be able to ship the libraries. Okay. So on each node before running your code, uh, Hadoop will basically copy all the jars over there. Okay, right? So here we talked about this part. Now testing a streaming job, testing a streaming job was comparatively easier, right? Because all you had to do is cat my file, pipe it to mapper, and then sort it, and then pipe it to reducer. That's all we had to do in case of Hadoop mapper, right? Sorry, streaming job. In case of a streaming job, that's what we had to do. So it, similarly, we could also test our Java code. Why do we need a testing framework? Because first, putting a test case onto a server and testing is resource intensive. If your code is not in good shape, there are chances that you will hurt the cluster. Okay. And for the argument's sake, let's say that we have a dummy cluster on which we run our MapReduce test. Still, the whole process the whole process of validating is too much time consuming. As we saw that we first wrote mapper, we then reducer, then we compile the code and then exported. I mean, compilation happened automatically. We exported the jar and then uploaded onto the server and then we ran it, right? So the whole process is, first, that doesn't cover all the tests. If there are corner cases, if there are various kinds of corner cases, then I mean, in any circumstance, you require a proper test cases in place. So you need to have a framework which can do the testing for you. Okay, and and thankfully the MR unit which comes with Hadoop does all of this job. Okay, so all you need to do is first create a dummy driver. Okay, MapReduce driver. If you see this MapReduce driver, it is the dummy. It's a the test case. It will execute your mapper reducer as if it is being run by Hadoop, while it's just a dummy driver which will execute your mappers and reducer. Okay, so you in the setup you do this, and then you start writing your test cases. Okay, in our case we have just written this. So let's have a look at what have I done. So let's go back to the step test. You can see here, first and foremost, create something called map driver, and then in the map driver I set my mapper, then reduce driver I set my reducer, and then I also create something called MapReduce driver. So map driver is only for mapper test cases. Reducer is only for reducer. If you want to test both simultaneously, mapper reducer, which is generally the ideal case, you use this. Okay, MapReduce driver. And now, when you want to test something, you tell MapReduce driver that this is my input, and and whatever after you run a MapReduce driver, you can get the output, and that's all. Okay. Similarly, here you could give reduce driver dot run. Okay, and that will basically, okay. So this will be the result of the reduce driver. And reduce driver, you can add the input again, add input value, and you can add the value. add input key. So add input key. Okay, here. Okay, here set input. Okay, you can set your input and the values. All right. So this way you can create the dummy test cases and then you can validate the result. Okay, this is your result. Okay, okay. So you can basically provide dummy input like here for testing for each test case, and then you can compare the results. Okay, if my result dot get is this much, then is it okay and all, right? So all of that magic you can do. So similarly, you can test the reducer separately as well as you can test both of them together. All right. So as we were telling you earlier in that while testing, you should always you should always test mapper separately, reducer separately, and then combine them and test them. And that is why there are three drivers. One is reducer driver, mapper driver, and then MapReduce driver. Okay. So whatever logic I wrote there, I just passed this input and ran it. And if you see this, let's have a look at, let's just let it fail. Okay. So two test case should fail and one should pass. And I'm saying JUnit test case, run it as JUnit test case. And if you see, it just gave me a nice word count. All right. In a minute of time, the word count of Sandeep Giri is here JKADD. Right? So whatever code you write over there, it can quickly be tested over here. All you need to do is, and a few of the more productivity hacks like here. So you can basically go to your JUnit and say run again. I'll run again. All right? You can quickly run again. And as and when you are writing your code, you can just keep on running again and again, and it'll keep on working. Okay, so as a thumb rule, when if you guys have not been working with JUnit, so whenever you're working on your product or any of the ideas, the general way is you write your all test cases even before you start writing your code. Okay, you just write a nutboard skeleton of your code and write down all the test cases and let these test cases fail in the beginning. Let all these test cases fail in the beginning, and you work as you code, you work towards making all the test cases successful. And that will give you really, really good feedback loop and you will feel great about it. And this is mostly I've coded. Okay. In the beginning days, I used to first write all of my code and make sure that it gives some output, and then used to write test cases for the heck of it. Okay, just to make my manager happy. But in real life, you should be basically coding against test cases. Okay, yeah. So you write down all your test cases, let all of them fail in the beginning. Let all of them fail in the beginning. And as and when you keep writing, they will become successful one by one. And generally that is the measure of how you are doing. Okay. That aids a lot to your whole manageability. Because if you write test case upfront, you are able to plan things. You are able to plan the whole product. In, okay. All right, moving on. So this is how you test your stuff. Now, if you see, we did not have to go back and forth here. If you see the console output, we got this result, right? Now, let's say we go back to our mapper. We change few things over here. Like for example, we do not do the lowercase. Okay? Now, if you see the result would be the result here would be this one has become the uppercase. Okay? And the moment you do this, now, okay, you see this? So immediately I get to see that what's going on here. All right? Okay. Sorry, I've already taken a break. Now, okay. Now we are going back to the question which we started with. Okay. Something called input splits. All right. So as we saw that in HDFS, each block is ruthlessly cut at 128 MB without caring about whether whether a word lies on the boundary or a sentence or a line. Okay, without caring about it, right? Now, but in Hadoop, whenever we worked, we always got a full word. We never got half word here and half word there, right? Which means there is something else going on, right? So on top of each block, there is a concept called input split. Okay, input split. Each input split is basically a subset of or a superset of or whatever you want to call it. Each input split is prepared out of one block or multiple blocks based on your need. Okay, in ideal condition, if you keep your input split close to the block size, it will be nice. Okay, in other words, you can visualize input split as number of lines. Okay, number of multiple lines. Okay. So Hadoop divides input into fixed sized pieces called blocks and fixed size pieces called input splits. Okay, and this sentence is not quite valid. There has to be not fixed size. This is not generally fixed size. Okay, pieces called input split. All right, and each input split is analogous to number of rows. Okay, and each input split contains multiple records, and record is analogous to a row in case of database speak. Okay, so input split is a subset of the whole file or whole content input, and it contains multiple records and has a logical meaning in terms of your code, in terms of your requirements. And for each input split, there is a single mapper instance, and map mapper runs map function of the mapper runs on each record of an input at a time. Okay, so input split contains multiple records, and each record is run against the input, right? Now, so did I make any sense till now? So each input split is like a subset of the whole file, maybe 10 lines, 15 lines, 20 lines, 100 lines, and so on. Okay? Based on based on how many lines were there in the in HDFS block, it created the input records, input split. Now, one HDFS block may not correspond to the input split. Input split is a logical unit and it is something which you govern. Say your program, let's imagine for time being that you are operating on binary file and all you want is when you execute your map function, you should get the whole binary file in a single shot. Okay? In one of the students' work, they needed to do a computation on image, and that whole image is required in one go, right? So in their cases, the input record itself, a single record itself, is equal to the whole file. There is only single record in the whole input split, and there are single input split for all the blocks available for that image, right? So it's a logical unit, right? It's a logical unit, but the most optimum part is that your input most optimum is your input split should be very closely related to the block, because if you have very small input splits, that means there will be too many input splits per block. Per HDFS block there will be too many input splits, and therefore when you are running it there'll be too much of data transfer, right? Because too much of overhead in the sense. Do we provide this split size in configuration? Will this be same for each node? Right. So this is what is something controlled by input splitter. I'll show you what does it mean by input split. Here, if you see, okay, not here. Yeah. Here, it's the input format class. The default input format class is what defines all of this. Okay. By default, it is text input file, input format, which means you will get line by line as a record and multiples of line as an input split, and and the whole file will be distributed uh, as usual. Okay. So so in that sense, by using Java code, input split is configurable. All right. Yep. So Vishal's point is that one file can be split from anywhere depending on the configured size. Yes. Can this not interfere? Yes, this will interfere. If the one word is split in between, the word count might increase. True. That's the reason why. So so that is why the concept of input splits has come other than HDFS block. Since HDFS block is split anywhere, is split anywhere. Okay. That is why on top of each block you create something called input split. Hadoop creates it for you using a input splitter called text input splitter, right? And that is where this whole concept comes into play. All right. So had the whole HDFS block been fed to your mapper, it could have been disaster. Before being fed to your mapper, it is converted into input splits and records. Okay. So here I'll just make this modification because no longer any of the instances of Hadoop keep this. Okay. Now Hadoop tries to run maps where data is located. We all know this part. If all nodes hosting replica of the data are busy, the maps executed at the same rack but different node. Okay. Otherwise, if that too is also busy, then the maps are sent to some other machines totally. Okay. So the good size of input split size should generally be close to the HDFS block. Otherwise, there will be too much of overhead. Okay. Now another visualization would be like this. So imagine that there is this block boundary, block 1, this is block 1, this is block 2, this is block 3. Block 3 is smaller because there is nothing else left. So imagine that you have cut the word here or you cut the line here, which means it will cause a problem. Therefore, the input split is prepared to have the whole word or whole lines. Okay. This is completely generic and can be programmed. All right. Similarly here. So you can see that it's not in the middle of the word, it's on the boundary. Okay. So can we keep any delimiters for this splitter ending next line or space? Okay, can we keep any delimiter? Yeah, you can keep. Yeah. So when you define these input splitters, right? When you define these input splitters, you can keep whatever you wish. Okay. You will have to define your input splitter. Right. This is a little complex. Okay, so question is what is rack? Rack is generally a local subnet on a same. So when you go to a data center, so you put a when you will see that there is a basically self shelf like a structure on which you put the computers. So each shelf or each rack, we call that shelf as rack also, is connected to the same hub. Okay, so they are the closest to each other. Okay. So whenever we say that we have got rack awareness, it means that we have got system which recognizes that these two computers are closer to each other and then these two computers are farther to each other. Okay, that is what is called rack. So a splitter input splitter is a code, basically a customization extension of input splitter abstract class, and you can implement this functionality. All right, I will give you an example of that one. Alright. Same thing again. So if you have got three lines, each of 25 MB, and say you have got 128 size, 28 MB size, or let me just double it for time being, 50, 50, 50. So each line is a 50 MB, although you never get to see such kind of files where each line is 50 MB. All right, all right. So this chunk, this block one, okay, we call it, let's say, block one, and this is our block two. Okay, so this line three is sliced strictly at 128 MB. All right, this line 3 is just sliced at exactly 123 MB, such that 28 MB 28 MB goes to block 1 and rest of the for line 3 goes to the block 2. Okay, that is input split. Now, so very good point, Srikanth. How do we come to a trade-off for input splitter size? Ideally, ideally, the input splitter size is something which should be defined by your business case, and then on top of it goes your optimization. Okay, on top of it goes your optimization. So while you are building a business case, say your business case allows you to handle the whole sentences at once, right? So you try to keep as many as sentences as possible, and such that your resembles closely input split resembles closely to the block size. Okay, to the block size. Okay, now if you have to define your own input split, okay, first you got to define something called input formatter. Okay, so once you have defined, so while defining input formatter, you need to extend this class called input format. Okay, you need to define this class called input format, and in this input format you define your splits. First is splits, get splits, and other is record reader. Okay, so to create your own input format, you extend this class called input format, and then you implement these functions, okay, or override these functions. In case you even want to change the definition of input split, you need to you need to extend this class and implement the two functions called the length and the locations. Okay, so this is how you generally. I have an example. If you want, I can walk you through it. So creating your custom record reader is something which requires a little bit of experience and knowledge. Okay. So let's say instead of one line at a time, I want my mapper should reduce to get three lines at a time. Okay. By default, our mapper was getting one line at a time, right? Now, let's say I go little cuckoo in the head and I realize that let's just implement three lines at a time. Okay, so what I need to do is first I need here I'm extending, note that I'm extending text input format. I can also extend directly the input format. Okay, if I extend directly the input format, then the input split also have to define, and then I implement a function called create record reader. There I send an instance of my own n line record reader. Okay, here the number of lines is 3, and in this I extend a class called record reader, and there I implement that how to get the next set of values for my mapper. This is a little tricky code, you should go through it, I'll just send it to you. Okay, under under my sg test, you will get sg dot custom reader. Okay, under that you will see these two classes. I'll send this code to you guys. This is not there in the default project. Okay, so basically, specifically this function called next key value pro- reads byte by byte into hdfs file and decide where to break the content. Okay, here you can say that break the content at a dot or full stop. It's up to you. All right, so this is how you implement it. I'll send it across to you guys. These two files are good enough for you. Okay, there we go. So in this manner you can create your own input formats. You can create your own input formats based on your requirement. You might want to process the whole binary. You want to process the file such that one paragraph at a time. Okay, so is everybody with me? Or so the process of creating this input format is important to know. And then once you look at couple of examples, you will understand what needs to be done, how to exactly split at a particular point. Yes. All right. So upload it onto the LMS and share it with you guys. Cool. All right. And each input is split further divided into records. Each map function is applied on each record. A record is a logical entity equivalent of RDMS in the row in the database. Okay. Input format creates records, such records. All right. All right. Now moving on. So this is clear to everybody, right? Do you have any doubts? You can ask me right away. So these boxes are your map code. Each input is split. Each input is split is passed to the map. Each record inside, record by record, is passed to map, and then our result is collected here and then sorted. Okay. Here is input is split. Remember, this is not HDFS block. Okay. I have tried to keep that silent. I did not explicitly mention it earlier, right? Otherwise, you could have got further confused at that point of time. So here, it's not HDFS block which is being fed to mapper. It is basically an input split which is created on top of HDFS block. Okay. Now, in this, if you once this all the result is gathered together and sorted, one this is the sorted result on all three, and then all of this gets merged here. Copying is happening, it gets merged here. Okay, actually the mic is quite closer and I am quite loud. So is my voice feebly audible to all of you? Because if I keep the mic too closer like this, all right. So All right. So after this merge happens, the whole input is fed to the reducer in case of a single reducer, and then it is put into HDFS. Okay. And then at the moment it is put into HDFS, the HDFS replication starts. Okay. So everybody is okay. The strong lines are basically these are the network transfer, and this is the local merging and transfer. Okay. Each of this is a node. Now, look at this diagram. This is little more complex, and but it will give you more clarity. So here you see there were multiple inputs. Here the input output of map is immediately split into two sections. Okay, two sections. Okay, and these sections basically, let's say the input is being split on the basis of male and female. Okay, so if you have multiple reducers, the split will start happening on each node. Okay, split will start happening on each node itself, and once that happens, one part of that split, not I'm not talking about input split here. Here I'm talking about separation of the keys. The moment map gives some output, and separation of the keys into two sets, because there are two reducers, it starts happening on the node itself. And once that separation happens there, both of these sections are independently sorted. Okay, so this is called partitioning. The moment you have multiple reducers, you need to do partitioning on each section, each mapper. And these partitions, first partition goes to the first reducer, second partition goes to the second reducer. And this is how, and again, the merging process happens just like before, and you get the output. All right. So this is how the multiple reducers work. Does this diagram clear? So when you have multiple reducers, right? When you have multiple reducers, as I said, the keys have to go to the same reducer, and therefore it is decided upfront on what basis the keys are going to be split. Okay. So by default, there is some partitioning logic. This is called partitioning. Okay, when you are having multiple reducers, you got to have partitioning, either the default one or yours one. So partition 1, partition 2. All right. Now, by default, there is only one reducer, and too many reducers. If you keep too many reducers, the effort of shuffling will be high. As you can see, if here there are two transfers happening, right? First section goes to the first reducer, second goes to second. Same is here, same is here. So how many transfer total? One, two, three, four, five, six. While here there was only three transfers, right? Now if there are five reducers here, so there will be total number of 10 transfers. Okay, so the transfer become num become as complex as number of reducers. Okay, if you have 10 reducers, then transfers become 10 times. So effort of shuffling is high, transport is high, and if there are too few reducers and your computation is heavy on the reducer side, then it is your single reducer will take a lot of time. So you will have to figure out what is the right one, right number of reducers for you. And it is completely your call. You may have to observe your task for some time and then figure out that my process is too heavy. Okay. One easiest way to do it is do a binary search. Okay. This is what I had done couple of times. So what I did was I ran my program first with single reducer, noted down the actual execution time as we did earlier. Here it shows you the here there is a CPU time actually. Here, CPU time spent. Okay, you note down this time with a single reducer. Okay, now the next step you do is increase number of reducers to 10. Okay, and then note down the time. Did it increase or did it decrease? If it decreased, then increase the number of reducers to 20. Okay, and do a binary search to get a point where exactly you get the minimum number of time. If you put 20, there are high chances that total time taken by the CPU will be higher. Okay, so or you can minimum number of uh, minimum number of reducer is 1, and total number of reducer you should keep is maximum number of reducer you should keep is node count. Okay, and you should do a quick binary search to figure out what works out well for you. Okay, even if you have thousand of nodes, it will take 10 at most 10 times of run 10 times run to basically figure out what is great for you, right? I generally do it like 1, 10, 20, 40, 20 and then 40 and so on. Okay, it will vary with that data, definitely will vary with data. So I'm saying that for your input, if you run your inputs daily or at periodic time for the same sampled input, this which you are expecting, you should you should try a binary search and figure out what is best. If your job which you are trying to do runs daily, that is the next optimization task. All right. All right. Now we have got something called partitioner. So partitioner is on what basis the keys on one reducer and other reducer differ. On what basis do they differ? What are the keys that should go to the first reducer and what are the keys that should go to the second reducer? That is something decided by partitioner. Okay, partitioner is something neat and clean, and interestingly, basically partition is something which separates the data. All right, so as soon as in this diagram this output of the map is actually being divided into two. This is what is being done by a partitioner. And here by mistake you got a partitioner. This is what a partitioner is. And this is what actually divided our data here, part 1, part 2. And you can see the last block. What do you see here? The last it has consumed till JW. So everything up to J has gone into the first reducer, and K onwards has gone into the second reducer. J has gone here, K has gone here. So here itself, here on the same node, you get keys starting up to J and keys after J. Okay? And how did it happen? Because we had created something called a partitioner. Partitioner, your partitioner extends partitioner, the partitioner, something defined by Hadoop, and then you implement a function called get partition. Get partition returns a number between 0 to the total number of reducers available to you. Okay, so what does it mean by total number of reducers available? This one. When you say total number of reducer task, okay, this is that number you get. Okay, so here this second value, this value is basically sorry, this value is basically total number of reducers. All right. So here, what am I doing is I'm saying if the key if the key key's length is greater than 0, then send it to the first reducer. If otherwise, send it to the second reducer. That is why if you notice this, here here not this one, in the part 1, you see this, you see this is the key with 0 length, okay, and it has gone to the second partition where k and above lies. All right. Why? Because we have said this. If the key's length is greater than 0 and key's first character is less than k, then return 0 means execute, uh, move these keys to the first reducer. Okay. And in otherwise send it to the first one. All right. Therefore, all the k and even the blank has gone to the second reducer. Make sense? This is how you define your partitioner. The and other one, I'll show you something nice, the one which I did recently. Okay. So here all I did was, because my key was just a single number, just a single integer, all I did was did a percentage and arg2. Okay. When you divide some number by a number, when you divide something by a number, the remainder will always be less than the denominator, right? And therefore it will be something between 0 to arg2 minus 1. What is the default behavior of the partitioning in this case, if there is no custom partitioner? Good, good. So when there is no custom partitioner, Hadoop assumes something and done some sort of a sampling to figure out what are your keys like, and then chooses something, some key which is in between. Okay. So the default behavior of partitioning is quite awkward in general. First it has to do sampling of your output and then it takes some call. You cannot ignore you cannot ignore some keys if you do not want them in our case. No, you can't do that. Why? Because here you got to return either 0 or 1 or some other number. If you return some other number which is not there, now that reducer is not there, then it throws an error saying that, um, while running it will throw an error that invalid reducer found. Okay. So this was interesting concept called reducer, and you will find it really nice when you use it. So the main role of reducer is, main role of partitioner is to segregate, to because you know your data better than Hadoop, right? You know your data better than Hadoop. Therefore, you can assist in optimization of the work. And most of the big data in most of the big data jobs require optimization. Only then you get some meaningful and time bound results. All right. So this is cool. Everybody's cool with partitioner? Yes. Partitioner come into picture only if there is more than one reducer. Very right. The default partitioner implementation is called hash partitioner. It uses hash code method of the keys module. Okay. No, I think this is a very good implementation, I would say. The way you have in Java, that and the hash code implementation is very different. I mean, how should I say? The hash code implementation, the default one is basically, I think, for 26 character based. It does a denominator just like this piece of code where we have divided the number per percentage by the total number of this, it does the similar kind of thing. It should be correct actually. It should be correct. I just don't seem to remember it. Okay. Because that's the way normal in Java, the hash code, the hash table, everything actually works in the same manner. Thank you, Naveen. Yeah. All right. So this is what it is. Now, there is another interesting concept called combiner. Combiner is actually cool. I just did some experimentation with and without combiner, and the results were really nice. Okay. So now what is combiner? So just after the map has finished on that node, you might want to combine the results before the transportation happens. Or you want to, you know, do something. Say you are trying to figure out the minimum out of some data, right? So if you find minimum on this map itself, right? Then it becomes easier to find the minimum, right? You will at the end of it, you'll have only three numbers to transport, right? In those cases, it is really interesting to have summarization on that node itself before the transportation is happening. So just after mapper has finished doing its job and sorting is going to happen, or sorting has happened already, you will you can run it runs your combiner function. If you specify a combiner function, it runs the combiner function to summarize the result on this node itself. It's similar to reduce, a little bit different. I'll talk about what is the difference. So it's like reduce on that same machine, reduce on that same machine, and that's what it does. Okay. Like for example, we did a character count, right, from A to Z and all that. In case we had summarized, we have done the character counting on on the same machine just after mapper have finished, it could have been really simple, right? It could have been really easy because the data transfer could have become just 26 numbers, right? So a combiner function basically runs on the node after the map has finished, and it processes the output of map, helps in minimizing the data transfer because it does a lot of summarization on the same node, and does not replace the reducer. Its role is different. It does not mean that there will be no longer you would require a reducer. All right. Now, now let's have something. All right. Now here we go. Cool. So the function which defines a combiner looks like it has got exact same footprint as reducer. Okay. But it has got one different property. Because it will not be applied on all the output, on the whole output of the mapper in a single shot. It will be applied on of the subsets of the output of the mapper, and that too multiple times. Okay. So it has to it has to be such a function which when applied on no matter how many values should give the result correctly. Okay. For example for example, sum, min and max, no matter how you apply them on a set of values, you will always get the same result, right? So max, if you apply max on 0, 20, 10 and 25 in single shot, you will get what? 25, right? Maximum of these four values is 25. Now maximum of 0 and 20 is 20, and maximum of 10 and 25 is 25. Now max of these two is 25, right? No matter in what manner you apply the max function on these values, you will always get the same result. Same is the case with sum, same is the case with count. Sorry, same is the case with sum, same is the case with min, and same is the case with maximum. But that is not true in case of average or mean. Why? Just look at this example. If you do average of two averages, the value is not same as compared to if you do the average of all the values in one sort, right? So basically a combiner is applied on the maps result in a on a different number of values at a time. Does it make sense to you? Are you guys with me? Input to a combiner is a single key but multiple values. Just just that multiple all values may not come together in a single shot and should for the combiner. Like here, like here, all four values came once, and sometimes only few values will come at once, and the other values will come at different times. Okay, and then it might get applied again and again. It's like your sorting algorithm. If you guys remember that when we sort the data, we divide in one of the algorithms, we divide an array into two halves. We apply sort on the first half and second half, and we keep on doing it until we get the final result. Similar way, a combiner function is also applied on the output of the map. Some value is one, some value is other. The result on the result, it is again applied, and we keep on applying it until we get a singular value. Okay, so combiner function always returns a single value. Input to a combiner is the intermediary data produced by all mappers in one node. Yes. Whereas input to the reducer is the output of all the mappers of all the node. Yes, perfect, you are right. But this intermediary data is divided into random subsets and given to combiner, and the result is again combined to give the output. Okay? Combiner comes before the Hadoop sorts in sequence. Yes. Actually, combiner comes while the Hadoop is sorting. Okay. While the Hadoop is doing a binary sorting, I mean, what do you call it? Divide and conquer kind of algorithm. That is when the combiner is also, the output is also passed to the combiner. So combiner actually gives a single value for that key. Okay. All right. All right. Most likely it comes just after partitioner. Okay. just after partitioner. This I need to actually study, that whether before partitioner or okay, combiner comes after partitioner or partitioner comes. Okay, so part 0, part 1, part 2 in the previous page will combine with either sum, min or maximum, for example. So this one, you're talking about this one. So part 0 will be after the summarization here. All right. Hmm. Vishal has got a point. Do we need a partitioner if we are using a combiner? You definitely require partitioner. You may not or may require a partitioner. Okay. All all this is making sure, this combiner is making sure that the values on a single node will become a single value. Okay. But the same, but still you will have reducer, right? And reducer might consume a lot of CPU, and therefore to decrease that load of reducer you might need a partitioner. Yes. So the partitioner will decide which reducer to send the single value to. Yes. Because there could be multiple values, right? For same key there could be other values also on the another nodes. It's up to you whether we. Right, right. You are right. Let me show you the actual usage of combiner. All right, I'll love to show you. So, do you remember our question where we were doing a frequency analysis of words, letters, right? Do you remember that? So here I wrote this one, this partitioner for that. Sorry, combiner for that. Okay. And what does combiner do? Combiner intermediately computes the summation of all the counts of each character. Okay. All it is doing is doing exactly what reducer was doing. Okay. This is what reducer was also doing. Reducer is also summing it up, and this guy combiner is also summing it up. That's all the values it's summing up, while the mapper is basically printing out one character per line. Okay, one character per key, and one as the value. That's what mapper is doing, right? Now here the combiner is actually doing this. Without and with combiner I did a little bit of statistics. I will show you this. Yes. Now let's see what happened to the CPU time. Okay, this part is without combiner. Sorry, this part, first part is without combiner. It took 23 seconds. Okay, and while the second part took only 12 seconds. With combiner it became 12 seconds from 26 seconds. Does it surprise you? Right, first the summation of characters is being delegated to combine to each individual node, right? Second, the data transport has been reduced drastically. Okay. Similarly, if you look at these data clearly, you will get to know a lot, right? So, are you okay? Are you all okay with combiner function? It's like summarization before you transport the data to the reducer. All right. Now we have got something else here. Here. So now we got this function f, a, b, c, and so on. And what does this function do is, so your reducer, sorry, your combiner function is basically doing a square root of a into a plus b into b plus c into c. Okay. So do you think it's a valid combiner function? Siva is saying yes. Anybody else? The way average was not a valid combiner function. Okay. Vishal, Madhav, all are saying yes. Srikant is saying no. Sanjay is saying no. Interesting. Interesting. So Sanjay and Srikant, what makes you think that this function is not suitable for becoming the combiner function? Try doing it on ABCD first and then AB once and yeah, I have muted. There's a bee in my room which is bothering me a lot. A big bee. All right? All right. So Sanjay, did you get your answer? No. Okay. So try to break it down this into multiple phases and try to do it multiple times. Okay. The way I have broken down max, the way I have broken down max. Right. So here, if you say square root of a square plus b square, then if you combine the result with c square, okay, let's see here. Okay. So we have got this. Okay. This is our result. If we all do all these things together. Now let's imagine that we do this first and whatever result comes, okay, let's call it x. And then in the next phase, we do x into x plus C into C, and that is square root of that one. Okay, and that will be equivalent to actually the result, right? So result 1 and result are same, right? Cool, cool. All right. So take a very close look at the combiner functions before making them combiner. All right. Sanjay is okay. Sanjay, are you convinced? Cool. Now the next one is the data locality optimization. Okay. What does the data locality optimization which we have been talking is? So imagine that you have this task, this colored blue colored task into HDFS block and the green colored as map task. So there are three cases possible. One, one HDFS block and map task both are on the same node. Okay. Second, both are on the same different node but same rack. And third, when they are on completely different rack. And fourth could be they are in a complete different data center. Map running on an HDFS block which is on a different data center, right? So this is called, okay. So out of this, the first one is the most preferable thing for Hadoop. Second one is the second most preferable, and third one is the least preferable thing. Okay, it will try its best to keep it close to the first one itself. Okay, keep keep node and the mapper on the same node as much as possible. It will try its best. Okay, few quick questions. Can reducer take the benefit of data locality optimization? Anybody else? This is called data locality optimization, sending the mapper code to the node which contains the data. No, actually, because reducer is generally reducer is generally a combination of all the data. So effectively, the reducer will have to move the data from one place to another. Yeah, then also it's no. But what Hadoop does in general is it tries to run the reducer on one of the nodes which contain the mapper. Okay, on the nodes containing one of the mappers, so that at least at least one transfer of the data is saved. Other than that, it can't do much. Yeah, but other than that, it doesn't take any other data locality optimization in place. Okay, so we don't really say that a reducer is actually taking any benefit from data locality because data transfer is anyway happening. All right. If you have to store a file with a replication factor of 3, on which all nodes will Hadoop store this file? Although this algorithm keeps on changing, but there is a definite pattern over here. So if you're storing a file with a replication factor of 3, it will be storing it on 3 nodes, right? Where all will it store? On the same data center, different data center, same racks, different racks? No. In no possible case it will keep the backup copy of the data on the same node. In any case, it won't keep. Otherwise, there is no point of having the backup. If you keep it on the same node, there is no point in having the backup. Okay. So the answer given by Naveen is correct. One on the same machine as the client as in when the client is trying to copy the data, like we are on Hadoop one, we have SSH into Hadoop one, and we're trying to copy the data onto HDFS. So one copy will immediately be kept on Hadoop one's HDFS, Hadoop one's data node, and rest one copy will go to the same rack but different machine. Same rack as in same subnet. Last number is only different, and the last one on different rack or maybe in a different data center. Okay. Okay. So it goes like this. The first one will be on the local node and other two will be off the rack. No, actually what Naveen is saying is actually correct. The strategy has changed. Okay. I'll update this. And this strategy has changed couple of times. Now, how does Hadoop know that what is the topology? So you actually define the topology in the form of directory structure A slash B slash D. Okay, and the distance between one node and another is basically the distance, the summation of the distance of the lowest common ancestor. Okay, node 1 and node 2, what is the distance? Quick. Who is the common ancestor? This guy is the common ancestor. The distance from here to here and here to here is 1 plus 1, 2, right? All right. Now, basically, you define this S1, R1, N1 based on the IP address and the name of the machine. So you give this new name to all your nodes, okay? And based on this tree structure, this is basically a tree structure: switch 1 rack 1 node 1, switch 1 rack 1 node 2, and so on. Okay, and based on this structure, Hadoop decides what is the distance between your node. Okay, this is called also called rack awareness. Understanding the networks as a tree is what Hadoop does, similar to the file path. And there is a file called DNS to switch mapping, which you can pass in the config script. In the config script, there will be a key called topo script, topology.script.file.name, and there you can specify your config file. A shell script which can translate an IP address into this tree structure. Okay, so yeah, name node has nothing much to do with this whole thing because we are more bothered about distances between the nodes, between the data nodes. Okay, because mapper is only going to run on data nodes, it's not going to run on name node. Yeah, in the config sites.xml, you will see the topology.script.file name. There you can specify what script to use to convert an IP address into this folder structure. Okay, and based on that, it decides the distance, and the distance is computed as sum of the distances from common ancestors. So quickly, so the distance between d1 slash r1 slash n1 is how much? 0, right? And distance between this and this, node 1, node 2, node 1 and node 2, same rack, 2. And and node 1 and node 3, quickly, node 1 and on the rack node 3, 4, right? Are you okay with these distances? So distance between, okay. So you can look at this diagram, S1, R1, L1. So distance between this node 3 and node 4 is how much? Node 3 and node 4? 4, right? 1, 2, 3, 4. If you start going from here, you'll reach here this way. While node 5, node 5 and node 4, no, it is 1 and 2. Okay, so that is how it is computed. And if you have two data center, you can do that. All right. So this is how the bandwidth is computed. Basically, this is how the distance is computed in Hadoop. Okay. So if you have got two data centers, there will be one more switch parallel to this one, and there will be a top node over there. Okay, so you'll go 1, 2, and above 1 there will be 3 and plus 3. Okay, this is only drawn for one of the servers. This diagram is only drawn for the one of the servers. Only this part. All right. So that's pretty much with respect to MapReduce. And you guys should actually finish all your assignments and submit it. Only few of you have done it. So please work on it. In case you are stuck, in case you require any help, drop me an email, schedule a time with me. We'll work it out and finish the whole MapReduce thing. MapReduce is probably the most important concept because starting with even the import tools, Flume and Scoop, they all use MapReduce internally. Pig, Hive, everything uses MapReduce internally. And the way most of these components are designed, they assume that you know how to optimize your MapReduce code. Okay? And once you have a clarity on MapReduce concept, then it would be very easy for you to give a reasoning why it is this way. Like for example, in Pig, while joining two tables, you can only join based on a key, right? You can't join on A greater than B value. And that's the reason why you need to understand what is going on inside. So if you have finished all these four assignment and also have gone through that matrix multiplication, then you should be fairly comfortable in converting any logic into MapReduce. All right, and also you will be able to visualize what's going in the head of pig, that pig Latin. Okay, so see you next week and have a great day. All right. Okay. Yeah. Vishal, can we have a discussion tomorrow? Actually, right now my wife is waiting, and it'll be difficult. All right. I'll give you a call tomorrow if you want, or you give me a call tomorrow anytime is free. Okay. Good night, Praveen, and thank you for the great session and great questions and answers. See you tomorrow, and all of you, please submit your assignments. Okay. In case you're stuck, let me know if you need any assistance from our side. I will you know dedicate some more time with you. All right. Okay. Good night then. Bye bye.